So in the last class we saw that the homogeneous linear system Ax equal to 0, it has at least this one trivial solution, right? So, and in the last class we also proved that if A is an n cross n matrix, then A is row equivalent to the n cross n identity matrix if and only if the system Ax equal to 0 has only the trivial system solution. Okay, so since A is row equivalent to the identity matrix, that means this is I can write this as I times x equal to 0, right? Where I is the identity matrix. And since A is a square matrix, that means so I is what? I is something 1, 0, 0, 0, then 0, 1, 0, 0, 0, 1, right? So this will be multiplied with the n cross 1 matrix. Let's consider x1, x2, lambda, xn. This is equal to 0. And if I write it explicitly, this follows that x1 equals to what? So if I take the matrix multiplication in the left hand side, this is just what? This is 0. x2 is also trivially 0, and everything xn equals to 0, right? Yeah. So that means this is the trivial solution of the system, and it is only true that if A is row equivalent to the n cross n identity matrix. Okay. Now today let us consider the inhomogeneous system. So a inhomogeneous system is something like Ax is equals to y. In homogeneous system of linear equation. So the first thing we here is important is that in the previous equation Ax equal to 0, it always has a solution, right? The trivial solution. But is it guaranteed that Ax equals to y, this system always have a solution? So that means from the previous one, this equation, we know that this system will always have a trivial solution, but for this system we are not actually guaranteed that this system satisfied solution. Okay, so yeah, even because if you set x to be trivially 0, then the left side is 0, but the right side is not identical 0, right? That's why this system is not the trivial solution is not the solution of this inhomogeneous linear system. Okay, so now what I can do is I can form a augmented matrix. Yeah.
So that is translated in any homogeneous system of A equations. You cannot have a trivial solution like this X.
Yeah. So when we are considering the inhomogeneous system, that means Ax equals to y, then does this system X equal to 0? So X is what? It is a, if I consider A to be a matrix of m cross n, and the size of A is m cross n, then X is what? X is n cross 1 matrix, right?
Yeah.
So now, if I consider this to be 0, 0, 0, 0, so n0, then the matrix multiplication AX, this is what? No, so for the matrix A, non-zero matrix A, if I multiply it with the 0, this n cross 1 zeros, then the multiplication is what? It is 0. But the system is defined by this, right? So the left hand side is 0, but the right hand side is not 0. That means this system is not. This system doesn't have a trivial solution. Okay. So now, so I can form a augmented matrix from this inhomogeneous system, and the augmented matrix is defined by so augmented matrix A prime. So I can construct the augmented matrix A prime from the inhomogeneous system Ax equals to y, and where A prime ij is defined by this is equals to Aij if j is less or equal n. Okay, so then, and A prime ij equals to yi if j equals to n plus 1. Okay, then so it is just something like A prime yeah. Is that okay?
Yes.
So A prime I n plus 1 equals to, this is equals to what? Y I, right? I just I just write these using the n plus 1 instead of j. Okay, so this is something like what? A11 yeah, so A12 dot A1n A21 A22 A2n AM1 sorry AM2 AMN this is the matrix A, right? And then the matrix multiplication will be something like x1, x2, xn, and this is equal to some y1, y2, yn, right? So what I did for the construction of the augmented matrix, I took this matrix A, then I took this m cross 1 column matrix, then I form A11, A12, A1n with y1, then A21, A22, A2n, y2, A m1, A m2, A mn, yn. Okay, so this is my augmented matrix A prime, and from this, as you can see, that this part is the matrix A, right? And this part is the m cross 1 column matrix, m cross 1 matrix Y, right? So that's why this definition A prime ij is equals to Aij if j is less equal n, because j runs from where to where? J runs from 1 to n. And there is also another element there, right? Yeah, one added column in the right. So this is the matrix A prime. Now, so and from a previous theorem, we know that every m cross n matrix is row reduced echelon matrix, equivalent to a row reduced echelon matrix, right? Yeah, echelon matrix. So then this A matrix, I can apply some sequence of elementary row operation to this A matrix, and I can form the row reduced echelon matrix from this matrix A, right? And let R is the row reduced echelon matrix that is equivalent to the matrix A. Okay, so that means I can apply a sequence of elementary row operation ERO on A, then I will find the matrix R, right? Now, so I can apply this same sequence of row operation, elementary row operation, in this column as well, right? Okay, then so after this EROs, after the application of these EROs, what I will get is some matrix R prime, where R prime is what? R prime, the first n column of this R prime is the n columns of R, right? Because I defined R is the row reduced echelon matrix that is equivalent to the matrix A. Then I perform the same row reduced EROs on this column, and that means what I'm doing is I am actually applying these EROs in this matrix, right? In this matrix A prime, and let R prime, so let yeah.
The arrow definition or assumption is so we are assuming that R is a row reduced echelon matrix.
Yeah.
For A, not A prime.
Yeah.
For A evaluation.
Yeah. So every m cross n matrix is a row is equivalent to a row reduced echelon matrix, right? We proved it in a previous lecture.
So this assumption we are taking for the matrix A, not A prime.
Yeah.
For A. But here we are doing the R prime for A prime.
Yeah. So the idea is okay. Let me just give us a few minutes. So this is the matrix A prime, right? So if I apply the sequence of EROs on this part, then I will get the matrix R, row reduced echelon matrix R. I can apply the same EROs on this column as well, right? And I'm considering then after application of the same sequence of EROs on the n plus 1 column, I can get the whole matrix R prime, where R prime is what? The first n column of this R prime is the n column of the matrix R, right? So, okay. Just consider this like A what? So if A is equivalent to R, then if I apply the same arrows on Y, this is what? This is some element of the field, right?
So then that will be given to R prime.
Yeah. So the whole things, let's just consider this is something Y prime. Then this is what? This is the R prime matrix. Is that answer your question? Okay. So that means okay. Let's just consider this to be not Z, Y. Consider it to be Z. Okay. Yeah. Okay.
So row reduced operations are
for block, but block just like what we did in block.
Yeah. No, I'm just using, yeah, you can take a block decomposition of the matrix and use that.
Block decomposition form.
Yeah, so that is exactly the idea. So now, as you can see, that R is a row reduced echelon matrix, right? So that means there are R number of, so if we can consider something like, so AX equals to Y is expressed, yeah, X equal to Y can be expressed as a linear combination of the system Rx equals to some z, right? So because this is this, and sorry, then I can write the system X equals to Y as a linear combination of the system Rx equal to Z, right? That means these two systems are equivalent system of linear equation, right? Okay. Then so R is what? R is the row reduced echelon matrix. So what I can do is I can consider if R has R non-zero rows with leading one of row I occurring in the Ki column, then what I can do is I can express the leading variable in terms of the free variable and how many leading variables I have for this. Since there are non-zero rows in this row reduced matrix R, that means there are leading variable in this system, right? And how many free variable in this system? In minus R. So in minus, yeah. So in minus R, free variable in the system. So that means what I'm having is I have R. Yeah. So I can the first column. Yeah. Yeah, Ki column. So I define the column as Ki because so as you can see 0, 0, 1, so 0, 2, 3, then 0, 1, so 0, 0, 0, 1, 0.
There is kind of index of the Ki.
Yeah. Okay. So that is the idea. So then let's just consider that what I can do is from this that Rx equals to Z, the first R equations. So these are equations. These are the non-zero equation for this system, right? So the first R equations of Rx equals to Z effectively express x k1. So since k1 is the column of first leading one, right? So that means xk1 is the first leading variable, then xk2 is the second leading variable. So what I can do is I can effectively express xk1 xk2 dot dot xk r in terms of the n minus r remaining free variable xj and the scalars z1 dot dot zr, right? Is that clear why there is also z1 dot dot zr? Because the system is rx equal to z. So for each non-zero equation there is a leading variable xj. There is also a constant, the element of the fields in the right hand side, right? So there are which z1, z2, and how many z there? There are mz. That means the size of z is what? The size of z is m cross 1, right? That means and the last m minus r equations are what? 0 equals to z r plus 1, 0 equals to z r plus 2, 0 equals to z m, right? Because in the left hand side, all these rows are 0 in the row radius matrix, right? So since all these rows are 0, if I multiply these rows with the n cross 1 matrix Ax, then this is what? This is just 0. But on the right hand side, there are m z. That means, so the system, and we know that Ax equal to y, this system is equivalent to the system Rx equals to z, right? That means the solutions are same for both these two equations, right? Now, so now when we will say that this system is actually have this solution? Only when these conditions satisfied. That means all these remaining z has to be 0. Okay. So that is the condition that the system Ax equal to y will have a solution. Okay. So let me give you this one. So as you can see, the first the first R equations. For the non-trivial equation, you can express the leading variable in terms of the free variable and the z, and how many z there are many, right? So right, but there are still m minus r equations, and that is what 0 equals to cr plus 1, 0 equals to cr plus 2, and 0 equals to gm. The system will only have solution if this condition satisfied. If this condition does not satisfy, then the system will never have a solution. Okay, so let me give you an example, and I think then everything will be clear. So let us consider the matrix A. So 1, minus 2, 1, 2, 1, 1, and 0, 5, minus 1. So this is a matrix A. Okay. So now what I can do is I can construct an augmented matrix, and I can consider some m cross 1 matrix Y, where Y equals to y1 dot dot sorry y1, y2, and y3. Okay. So the system Ax equals to y. I can construct a augmented matrix from this system, right? And what will be the augmented matrix A prime? A prime will be, okay, so 1, minus 2, 1, 2, 1, 1, then 0, 5, minus 1. Now, sorry, and there is a y1, y2, y3. Okay, is that clear? Okay, so I can construct, so I can apply the EROs in this augmented matrix A prime, right? So the first row is already the first non-zero element of A prime is 1. So I don't have to do anything with this row then, but for the second row and third row, what I can do is I can perform EROs like minus 2 R1 plus R2 equals to R2 prime, and so there is also a 0 in the bottom, so I don't have to do anything for this as well. So after applying this operation, row operation, so this like 1 minus 2, 1, y1, then this is 0, this is 5, and this is minus 1, I guess, yeah, minus 1, and this is y. So I multiply by minus 2, then y2 minus 2y1, and 0, 5, minus 1, and there is y3. Okay, so this is the first row. Then for the second row, what I can do is I can, no, for the second row I have to use 1 over 5 with R2 to then I will have the for the leading variable in the second row, leading 1 in the second row, then this is R2 prime, and this is something like 1 minus 2, 1, y1, and 0, 1, minus 1 over 5. Yeah. Then y2 minus 2y1 over 5, and 0, 5, minus 1, then y3, right? Then what will be my next step? Yeah. I have to make this minus 2 and this 5 0. Then what I can do is I can multiply 2 with R2 plus R1 equals to R1 prime, and minus 5 R1 R2 plus R3 equals to R3 prime. Then this is like 1, 0, and 2, right? So 1 minus 1 over 5, that is equals to, so 1 minus 2 over 5 equals to 3. So this is 3 over 5. Does it make any sense? So 2 or 2 minus, yeah, 3 over 5, and then y1 plus 2y2 minus 4y1 over 5, and then this is equals to 0, 1 minus 1 over 5, and y2 minus 2y1 over 5. And for the last one, this is 0, also 0. This is like minus, yeah, this is also 0. And the last one is y3. y3 with y3 minus y2 plus 2y1. Okay. Now, so as you can see, this is already in the row reduced form, right? So, and this is the equivalent system of Ax equal to y. And now, this system will only have solutions if y3 minus y2 plus 2y1 equal to 0. If these conditions satisfy, only then the system Ax equals to y will have solution. Otherwise, it is not possible that the system have solution. Okay. So, do you understand it? Okay. So, what will be the solution then? The solution will be like x1 and 3 over 5 x3 equals to y1 plus 2y2 minus 4y1 over 5. Okay, so just simplify it. This is y1 plus 2y2 over 5. Okay. Then for the second one is x2 minus 1 over 5 x3 equals to y2 minus 2y1 over 5. And for the third one is it is already 0. So the solution x1 is equals to minus 3 over 5 x3 plus y1 plus 2y2 over 5, and x2 equal to 1 over 5 x3 plus y2 minus 2y1 over 5. Okay. So here we see that the first equations of Rx equal to Z effectively express all these leading variable in terms of the n minus r remaining free variables xj and the scalars z1 to zr. And as you can see, these are the some scalar y1, y2, y3. These are some scalars, right? So, and as you can see from the solution that this is what x1 is a leading variable here, right? And I write x1 in terms of this free variable x3 and these scalars y1, y2, right? Similarly, x2 equal to 1 over 5 x3, where x2 is the leading variable and x3 is the free variable, and these scalars y2, y1. Okay. Then, yeah.
leading variable.
Yeah, x1 and
bounded variable.
so x1 and x2 are the leading variable because in the r number of columns, sorry, r number of rows, there are only one on that. The first element is the only one, right? The first element is the non-zero element is the one. So now just consider this type of equation that ax plus by.
I'm just trying to understand what is the interpretation of leading variable. So is it kind of a bound variable? Because you're saying x is free variable, right?
I mean, it follows from the as you can see, x3. These are the variables that can have any
Anyway,
values, right? So these are free to choose. It is up to you that you can assign any value to this variable. That's why we are calling these variables as free variables. But you cannot assign any numbers, any arbitrary numbers to this variable x1 and x2.
kind of bounded.
Yeah, that's why we are saying this to be the leading variable. And the leading comes from the fact that in the row reduced matrix, there are only leading one in a row. That's why. Okay, so these are the so this is a solution of the system x equal to y, and you can exercise some problem from the Hoffman and Kunz. The problems are from page 15. Problems 1, 2, 3, 4, 5, 6, 7, and 9. Okay. Okay. So yeah.
Before the point where we wrote about say,
Yeah.
can you please scroll up?
Saved this.
A little bit down.
Okay.
Yeah. The last, you are stating that the remaining variables, like say in our case we have y3. You are stating that from our definition y3 has to be 0.
No, y3 doesn't has to be 0 because after taking the EROs on this augmented matrix, we end up with y3 minus y2 plus 2y1.
Remember, I think it was written there, said once after EROs. Yeah, that, oh, I get it.
Do you understand it?
Yeah.
So I get this z after taking the EROs, right? So so the first system was what? Ax equals to y. After apply the EROs, I get the system Rx equal to 6. Right? That means these z are not equivalent to y. Z is not equivalent to y.
No.
Yeah. Right? So that's why y3 is not 0, but this y3 minus y2 plus 2y1, this is equal to 0. Right? Okay. So now let us okay, so now let us discuss a new topic, that is interpreting matrix multiplication AB as linear combination of the rows of the matrix P. Okay, so let's try to motivate this definition. This is
I have a comment on what James showed a while ago. Can you please go above
This.
where he wrote this y3 minus y2 plus 2y1 is equal to 0? Can you go a little above? So if this is not equal to 0, what can you conclude?
The system equations don't have a solution.
Yeah. Yeah.
So it is called a consistency condition for the system to admit solution. If it is not equal to 0, it means that the system does not admit any solution. So in this, so if y3 minus y2 plus 2y1 is not equal to 0, these non-trivial, it's this inhomogeneous system of linear equations will not admit any solution. So you can see in this example that an inhomogeneous system of linear equations may not have any solution at all, whereas in contrast to an inhomogeneous system of linear equations, a homogeneous system of linear equations always admits a solution. That solution is the trivial solution. And this example shows that an inhomogeneous system of linear equations may not have any solution at all.
Okay. Okay. So let's start with this A11, A12, A21, A22 with B11, B.
Rows of P or columns of P?
What is the question?
Combination of the rows of P or columns of P?
Rows of. Okay. So B11, B12, and B21, B22. So I just take a simple two matrix A and B, and that is a 2 plus 2 matrix. So what is the matrix multiplication of these two matrices? This is equals to A11, B11 plus A12, B21, and A11, B12 plus A12, B22. Then this is A21, B11 plus A22, B21, and A21, B12 plus A22, B22. This is the matrix
I
multiplication.
think there you put 3 2's.
Yeah, sorry. Okay. So this is the matrix multiplication of these two matrices A and B, right? So I'm just considering here that this is the matrix A and this is the matrix B. Okay. So let's consider this that so there is a A11 here, right? And there is a A12 here. And there is also a A11 here and A12 here, right? So what I can do is like I can write A11 and there is a B11 and there is a B12, right? So I can write it like B11, B12 plus A12. So there this B21 and this B22. B21 and B22. This is the first row, right? And the second row is A21, B11, B11 and B12 plus A21. Sorry, I think this is A22, B21, B22. I can write the matrix multiplication in this way, right? So this is exactly the previous matrix, this one, right? So you can multiply A11 with B11 and A12 with B21. Then you can add these two, because this is what? This is a 1 cross 2 row matrix, and this is also a 1 cross 2 matrix, and so the addition is possible in these two matrices, right? Okay, that means this is what? This is just I take the linear combination of the matrix. Yeah, so the multiplication is actually what? The linear combination of the rows of the matrix P, right? Okay, so in general, for an arbitrary matrix, when the matrix multiplication makes sense, so I can do A11 dot dot A1n, A21 dot dot A2n, AM1 dot dot AMN, B11 B12 dot dot B1P, B21 B22 B2P, BN1 BN2 BNP. So the multiplication is possible here in these two matrices, right? Because this matrix has a n columns and this matrix has a n rows. That means the multiplication makes sense, right? Now, so what I can do is I can write it like A11 A1n A21 dot dot A2n AM1 dot dot AMN. Then I can consider it like beta 1, beta 2, beta n, where these betas are the row of this matrix, this, and others, and the last one is P n1 dn2 dot dot dnp, right? So the matrix multiplication will be what? This is equals to A11 beta 1 plus A12 beta 2 plus A1n beta n. Then again A.
Can you make the tail of the beta a bit longer? Then it looks like beta.
Oh, okay. So A21 beta 1 plus A22 beta 2 A2n beta n. Then the final one is AM1 beta 1 plus AM2 beta 2 plus AMN beta n. Right? So I can interpret the matrix multiplication in this way. Okay. So let's consider a theorem here. So I'm not going to give you an example for this. You can definitely do one. And let's just consider this example: 1 3 2 2 2 1 and 2 3 1 1 1 2 3 2 2 1 2 0. So you can check this multiplication. Actually, you can interpret this multiplication in the above fashion. I mean, in the linear combination of the columns of rows of this matrix. Okay, the later matrix. So let's consider the theorem. So the theorem is, if A, B, C are matrices over the field F such that the product BC and ABC are defined. Then so are the product AB and AB, C and ABC is equals to ABC. Okay. So when I say the products BC and ABC defined, what does that mean?
That is matrix multiplication is possible.
Yeah, the matrix multiplication is possible. That means actually, so let's just start the scratch of the proof. So I have to consider, so let B is a matrix of B is an M cross N matrix. Okay. Sorry. So the number of row in C is what? Is
So second cross B.
so sum N cross.
A cross B.
So the number of rows in C is N, right? And what is the number of column in A? It has to be M, right? Now let's just consider A, B, C and the ij element of this product, and this is equals to, so I can start with r equals to 1, the down variable, and this is A I R. So let me check, this should be M because yeah, this should be M. Then BC is R J, right? Does it make sense? Yeah. Why it is M? Because the number of
Number of columns.
A is M and the number of rows in BC is M, right? So that means this is actually makes sense. Then what I can do is I can expand this one as well, right? And then this is R equals to 1 to M A I R summation of K equals to 1 to, this will run till, and what will be the limit for K equals to 1 to, no, no. So you have to consider the matrix multiplication BC. So the number of column in B is n, and number of rows in C is also n. That means this will be n, right? Okay. So that means this is B R K C K J. So I can take the summation out and I can write it K equals to 1 to n, then R equals to 1 to m A I R B R K C K J, and I can bracket it.
Yeah, but at this point,
Yeah.
you can group
Yeah.
these three scalars. These are entries from the field, right? AIR, BRK, CKJ are all entries from the underlying field. And you can group them whatever way you want, right? How can you do that? Follows from what? One property of field, which is what?
Which one?
Associative. Very good. Associative. That allows you to do that, right?
Yeah.
So here we invoke the associativity property of a field to do that. Okay. Thank you.
And also this is a finite summation, right? R equals to 1 to m. That means there is no issue with the convergence. So that means this is what this is, K equals to 1 to n, and A I sorry A B I K with C K J. So this is this, right? Does it make sense why I did this in this way? This is the definition, right? Okay. So this is equals to what? Then again, this is equal to AB times C with I J. So this K, this is the summation index. Previously here R is the summation index, and that's why I can write this whole terms by this one, right? Okay, so that means A times BC, the element ij of A times BC is equals to AB times C. And there is a remark here, and it says the relation ABC is equals to ABC implies that the linear combination of linear combinations of, so the left hand side I take the linear combinations for this part BC. I take the linear combinations of the rows of C. Then again for the whole ABC, I take again the linear combinations of the rows. Yeah. So linear combinations of the rows of C are again linear combinations of C. Why? Because on the right hand side, this is a matrix and this multiplied by C, that means I take the linear combinations of the rows of C on the right side, right? Okay. Yeah. Okay, so there is one important thing here follows, that if, now I'm considering this, if B is a given matrix C and C is obtained from B by means of an elementary row operation. So,
C is obtained from by means of
From B.
sorry,
B is
from B by means of an ERO. Then every row of C can be expressed as a linear combination of the rows of B. Hence, there is a matrix A such that AB equals to C. Okay, so this is saying that if B is a given matrix and C is obtained from B by means of an elementary row operation. Okay, so then every row of C, the matrix I obtained from the matrix B by applying the elementary row operation on the matrix B, then the rows of C can be expressed as a linear combination of the rows of B. And so, does it make sense why this is possible? Or so, yes, I'm going to define the elementary matrices.
so because C is obtained from B.
Yeah. So a simple idea can be like, so when we consider a system of equation x equal to 0, so I can take the linear combinations of that system x equal to 0 and form another equivalence system, and the equivalent matrix, if the equivalent matrix is P, then Ax equal to 0 and Bx equal to 0 will have the same solution. We know that this year, right? So, and in the previous theorem, sorry, in the previous, in this section, we saw that it is possible that matrix multiplication can be interpreted as a linear combination by the second matrix, right? On the second matrix. So if B is a matrix and C is a matrix that can be obtained from B by an elementary row operation, then the rows of C can be interpreted as a the linear combination of the matrix P. Okay, so this is a very important concept. Why? Because we are going to define the elementary row operation. Elementary matrices. Okay, so so as we know that there are 3 elementary row operations, right? And we can define, so the definition, let's just first define this definition.
So it tells you that in the previous case where Jim wrote AB equal to C, initially you started with this matrix P, right? And you got to that matrix C by a finite sequence, no, just one elementary row operation. You got to C from B by applying an elementary row operation. So this is a matrix multiplication version of that single elementary row operation, which means that whenever C is obtained from B by a single elementary row operation, you can find a matrix A such that AB will produce C. It is the case.
That means there is every row operation is equivalent to matrix.
Matrix multiplication. So this is the matrix multiplication version of a single elementary row operation that will motivate him to define elementary matrices, like he said. Now he's going to define elementary matrices.
And M cross M matrix is said to be an elementary. So elementary matrix if it can be obtained from the M cross M identity matrix by means of a single elementary row operation. So this is the definition of the elementary row operation. So let me give you an example, then you can see why this is like this. So the third elementary row operation, what was that? So we exchange the rows. So let us consider the 2 cross 2 identity matrix, that is 1 0 0 1. Okay, then if I apply the third elementary row operation on this matrix 1 0 0 1, this will be what? This will be 0 1 1 0, right? So this is the third elementary row operation on the matrix 1 0 0 1. Now let us consider another matrix A1 1 A12, A21, A22. So if I take the third elementary row operation in this matrix, this will be what? A21, A22, A11, A12. Right? So we know that the third elementary row operation is what? It is exchanging the row. Like the third one is defined as E of A ij is equals to A ij if j is not I is not equals to R and I is not equals to S. Then E A Rj is equals to A Sj and E A Sj is equals to A Rj. Right? So this was the third elementary row operation. Now, so and I applied this third elementary row operation in this matrix. Right? Yeah. Yeah. So, but let me check that I applied the third elementary row operation on the identity matrix and I got 0, 1, 1, 0. And now if I multiply it with A11, A12, A21, A22, this will be what? Take the multiplication and see what will happen. This will be, so this will be A21 and A22, A11, A12, right? So we define the elementary row operation as a function, but we can associate with each elementary row operation with a elementary matrices, right? And as you can see from this definition that after the application of the third elementary row operation on the matrix A11, on the matrix A, I got this matrix, right? And this is also equal to, this is also true if I multiply, if I take the third elementary row operation on the identity matrix, on the 2 cross 2 identity matrix, then if I multiply it with the matrix A, I got the same result, right? So this is one example.
So you can write it like, equal to E of here.
So
here.
So this is 0, 1, 1, 0 multiplied by
So this is equal to
okay
E of what?
the matrix.
No, the whole matrix.
Yeah. Okay. So
That way,
A11, A12, A21, A22.
Okay, so that associates. So this way you see that just look at the first line and the last line. So E applying on that matrix is the same as multiplying that elementary matrix with the same matrix.
Right.
So elementary row operation
Can be interpreted.
Action of the elementary row operation can be seen as multiplication by the corresponding elementary matrix. That's what we can see from here.
Yeah. Yeah.
A little bit out. If there is m cross m, that means square. That means it always has to be square.
Why? So in the definition, Yeah.
In the first an m cross n matrix, that means it always need to be square because we have
So
that operations for rectangular matrices also, right?
no, because it can be obtained from the identity matrix.
So I'm saying an m cross n matrix.
Yeah. So it is possible you can define matrix like this, but we are not interested on those matrix. We are interested actually in this type of matrix that you can form from the identity matrix. Okay.
Yeah, but that means this operation is only limited for square matrices.
No, you can actually take the like some other form of this matrix, right? But those are not defined as the elementary matrix. The definition of the elementary matrix is if you take the ERO on a identity matrix.
I think I got his question. So can you please go down?
Okay.
I think what he asked is the following. So in the first line, can you take a 2 times 3 matrix on the left hand side so that the multiplication is also defined in that case? Do you understand what I say?
2 times 3 or 3 times 2?
No, 2 times,
Something with column
2 times 3. Yeah, so
Okay,
I'm
so you are
suggesting A11, A12, A13, then A21, A22, A23.
Okay.
Okay? So that way you have this multiplication defined, right? Because you have 2 times
So
2 matrix.
okay, I think I can, if I write, then it will be so. This is, I am considering A11, A12, then A13, A21, A22, A23.
And do the multiplication, see what you get.
You make the same. You reverse.
Is that clear?
That means that
It works, right?
Yeah,
It works then.
that means in the definition we can have m cross n also.
No. Because for the definition of the elementary matrix, you cannot change that. Because that D0110 is obtained from 2 times 2 identity matrix. So that cannot be reversed. But that acting on the matrix should not be limited to square matrix. Okay,
So-
which means that you can always interpret a single elementary row operation on any matrix of any size as multiplication by elementary matrices. Right? This was your question?
Yeah.
Yeah. So in that case, in that first thing, that m cross m will not change because it is obtained from the identity matrix. And once you get this elementary matrix, you can interpret any elementary row operation on any matrix by multiplication by one of these elementary matrices.
So, yeah, I think I have another comment with this because it is not just this one matrix that can be give you your desired matrix. You have to apply a sequence of these elementary matrix on the matrix from which you are going to obtain your desired matrix. Okay. So then let's first consider this. Now let us consider the theorem. So theorem. Let E be an ERO and E be the M cross M elementary matrix E equals to EI. Then for every M cross N, so what you just asked a few moments ago, M cross N matrix A is actually E of A equals to E. Okay. So as you can see that the size of E is M cross M, but the size of A is M cross N. Okay. So that means if I take the elementary row operation E, I mean the E of A is equals to the multiplication E times A. Okay. So I can give you a scratch of the proof here. So
Oh, here you see A is
yes,
M times.
that's what I can say. So let us consider the second type of ERO. Okay. So for the second type of ERO, we know that E of Aij is equals to Aij if I is not equals to R, and E of A Rj is equals to A Rj plus C times A Sk. Sorry, Sj. Okay, this is the second type of elementary row operation, right? Okay. Then now let us consider. So E is equals to what? E is equals to Ei, right? Now then what is Eik? This is equals to E of I with Ik, and this is equals to delta Ik if I is not equals to R, right? Everyone is familiar with Kronecker delta Ik. Do you know the definition? Okay, so delta Ik is defined as definition is delta Ik 1 when if I equals to k, 0 if I is not equals to k. Okay. So you can interpret a identity matrix in terms of the Kronecker delta. So that means Eik is equals to delta Ik if I is not equals to R. Now then what will be ERK? ERK is E of I with RK, and this is from the definition we know that this is delta of RK plus C times delta of Sk, right? This was the definition of ERO, second type of ERO, and this is from that we can deduce this one. So ERK equals to delta RK plus C times delta Sk, right? Then what is EA of Ij? We know that this is equals to summation of k equals to 1 to, the summation will run from 1 to m, because this is a m cross m. That means this is E I k with A, K, J. And what is the definition of EIK? This is when I is not equals to R, this is just simply delta IK, and when ERK is equals to delta RK plus C times delta SK. So this is like summation of K equals to 1 to M. So EIK, if I is not equals to R, then this is just what? Delta I K with A K J, and this is equal to what? So the K runs from 1 to M, and delta IK is just 1 at that when I equals to K. That means this is equals to A I J if I is not equals to R. Okay, but again there is another definition for EIK, and that is K equals to 1 to M delta of IK. Okay. So RK plus C times delta of S. If I multiply it with AKJ, then this will be what? It will K equals to 1 to M delta RK AKJ plus C times delta of SK with AKJ, right? Then this is equals to what? This is equals to RJ plus C times A SJ, right? Then so I can collect all these results, and I can write E A I J is equals to A I J if I is not equals to R, and A R J plus C times A S J if sorry yeah if
It's just I is equal to
I
R.
equals to R. And from the definition, so did I write it? Yeah. So from the definition, we see that E of Aij is equals to Aij if I is not equals to R, and E of Arj equals to Arj plus C times Asj. Right? So from here we conclude that Ea is equals to E of A, where the size of E is M cross M and size of A is M cross N. Okay.
So it can be done for the other types of
Arrows as well, and you can check it. So let me give you the last theorem. Sorry, this is a corollary from the theorem. Corollary. Let A and B be M cross N matrices over the field F, then B is row equivalent to A if and only if B equals to PA, where P is a product of M cross M elementary matrices. So I'm not going to prove this theorem. I'm going to motivate what is the proof behind this. So when we say a matrix A is equivalent to another matrix B, what was we considered when we defined the equivalence of two matrices? So we considered that the matrix B can be obtained from the matrix A by a finite sequence of elementary row operations, right? That was the condition. We defined it on that way. And from the previous theorem, we see that EB and ERO and EB the M cross M elementary matrix, then E is equals to what? EI. Then for every M cross N matrix A, EA is equals to EA. So that means we took finite sequence of ERO, and for every ERO, I can construct a elementary matrix, right? And for the finite sequence of ERO, what I can do is I can multiply each elementary matrix for each ERO, and I can obtain the matrix B from the matrix A, right?
So that tells us that matrix P is just a multiplication of certain elementary matrices, right?
Yeah. So this B equals to PA, that means B equals to PA, where P is equals to some, let's consider EK minus 1 dot E2 E1. So this is B is equals to EK minus 1 E2 E1 multiplied by this. Okay.
So that E1 of A will give you one elementary row operation acting on A, and E2 of E1 of A will give you the second elementary row operation acting on E1
So,
of A. So,
and there is a very simple way to look at it, right? So, because I ask you to prove that ERO is actually so equivalent matrices are what? These are the equivalence relation, right? This is the equivalence relation. So that means E1A. So the third property of equivalence relation is what? That is the transitivity, right? So, and the transitivity is actually what? If A is equivalent to B and B is equivalent to C, then A is equivalent to C. So, from this definition, it says that if E1, so A is the original matrix here, and if I multiply it by E1, then this will be the equivalent matrix of A, right? So that means E1 A is equivalent to A. Then if I apply again another elementary matrix from the left, then this will also be equivalent to A. And since this is a finite sequence of multiplication, that means this is what? This is the equivalent to the matrix A. The final matrix B is equivalent to the matrix A, right? Thank you very much, everyone.